Hello again, everyone. Welcome to our discussion of section 4.5, where we will look at solving exponential and logarithmic equations. Everything we've learned so far, the properties of logarithms and natural logarithmic expressions, every technique we've learned since we began talking about the log and natural log expressions and exponential functions in this chapter, everything converges into this section. This section is the pinnacle of this chapter, and it is the convergent point for all the skills we learned in this section. Very, very important section this is. After this, in fact, we will go to another chapter. I believe it's chapter 10. So this last section summarizes all the skills we need to know about logarithmic and natural logarithmic expressions. So here I have put together the logarithmic laws that were discussed in section 4.4. We need to know those. We need to remember them. And the other statement that I made a couple of videos ago, that logarithmic functions, this goes for natural logarithmic functions as well. The logarithmic functions generate or produce an exponent. If you forget that, it causes a lot of problems when you try to solve logarithmic or natural logarithmic equations. So please, that's a very short sentence. The log functions and the natural log functions are the only function in mathematics that do this. So please remember it. Log functions and natural log functions generate an exponent. Okay, and if you have to involve logarithmic functions, you must take the log of both sides. This is critical. So just like, remember when we solve equations, you add or subtract the same value to both sides, right? You don't do one thing to one side and not do it to the same thing to the other, right? If you multiply, for example, if you want to clear fractions, you multiply both sides of the equation by the same number. Let's say 3, to get rid of a fraction, okay? The same way goes with logs. If you have to solve one side for x and you have to take the log of that side, you can't just take the log of one side and not do it to the other side. You must take the log of both sides. Okay? If that's the technique that you're going to be using, you need to take the log of, or natural log of, both sides. Just remember that. Okay. So we begin. Here, we have 10 to the x equals 25, and we want to solve this equation for the value of x, which means we need to isolate x. Now, in order to solve for x, we need to ungroup it from 10, because right now it's grouped with 10. As what? As an exponent. Right now, x is an exponent of 10, and that's a group. So we need to ungroup it. To do that, we need to take the log of the left side. So log of 10 to the x power, we need to do that. In order to bring the x down, remember that property? That once we have the log of some number to some power, we can bring the power down and in front? That's why we're doing this. But we can't do this and not do it to the other side. So we have to take the log of the other side as well. Okay? So now we can achieve what we set out to do. We can isolate x by we can ungroup it. So x times log of 10 equals log of 25. Now the base here is missing, right? It's not written. What did we say about log functions with a missing base? That means that base is 10. So what do we know about log of any number to the same base as that number? That equals 1. We talked about it last time, right? So this whole thing is equal to 1. So on the left, we have x times 1 is x equals log of 25. Now, if you're doing this on an exam, in class, on campus, and your instructor says you cannot use the calculator, that is the final answer. So you stop there. But if coordinators all of a sudden decide to allow you to use the calculator, or if this is a problem in the homework online, you can use calculators, right? So let's figure out what that number is. So we'll give answers in both ways. In this form, which doesn't require the use of a calculator, and also in the form where it does require the use of a calculator. So here we have the log of 25. This is the log key on my calculator. Log of 25, close parentheses, enter, and we have that. So if this is me, if I'm taking this exam or I'm entering this on some computer in an online homework management system, I would say 1.3979. Unless the computer program says, hey, round your number to 3 decimal numbers, or 2 decimal numbers, or 1 decimal number. If it says 1 decimal number, you would say 1.4. If it says 2 decimal numbers, you would notice that 9 has a 7 after it, and if you round it up, you get 1.40. So 1.400, okay, or 1 however many decimal values they ask you to round it to. But I'm just going to round this to 1.3979, so 4 decimal places. So, or x equals 1.3979. Okay. So give this answer if you're not allowed to use a calculator. Give this answer if you're allowed to use the calculator. So do you see why we've been studying log functions so far? It's for this reason. So we can solve equations that involve logs. So far, we didn't know a technique. Now we have a technique. Okay? Or a set of properties. Okay, here we have 5 to the x power equals 4 to x plus 1 power. Well, the variable for which we're solving is in the exponent. So we have to ungroup that exponent or that variable from the base. How do we do that? What's the technique to do that? We take the log of both sides. Okay, if the variable that you're solving for is in the exponent, you have no choice but to involve log or natural log functions. Okay, so let's do that. We're going to take the log of both sides. Log of 5 to the x equals log of 4 to x plus 1 power. And please, if you haven't done this already, pause the video, solve this on your own, and then come back to the video after you have your own solution in front of you. Okay, again, it does not matter if your solution is wrong. What's extremely important that you give yourself the opportunity for your mind to solve this on its own. Okay, that's what is important. All right, so now we have a property in mathematics that says that we can, once we have logs, we can bring the exponent down and in front. So here, I can write x times log of 5. I got to be careful here on the right-hand side, because when I bring this down, I better put a parenthesis around it, because that exponent must distribute itself to all of this. Both terms, not just one term. So I've seen a lot of people make this error. They say x plus 1 log of 4. Guess what's the error here? Well, they forget to put the parentheses around this, and what that means is that they're going to multiply log of 4 by just 1 and not by x, and that's a huge error. Okay, so please don't forget, if you have multiple terms in the exponent, when you bring them down, you got to put the parentheses around them to indicate the distribution or multiplication by everything else that comes after it for both of these terms. If I had 3 terms, I would put the parentheses around all 3 terms to indicate that all 3 terms must be multiplied by log of 4. Okay. Now let's simplify this by distributing on the right side. So we have x log of 5. I could calculate this with my calculator right away, but I want to give both answers. One without use of a calculator and another answer after we use a calculator. Okay, so x times log of 4 plus log of 4, right? I distributed the log of 4 into both terms that were part of the exponent. So we're solving for x. That means we need to isolate x. So I need to take this log of where we have another x on this side too. So let's put both terms that have x in them on one side. So x log of 5 minus x log of 4 equals log of 4. Okay. Now what? What do I do now? Well, if you said factor the expression on the left, you're absolutely correct. So factor the expression on the left, x log of 5 minus log of 4 equals log of 4. Okay, so now we're solving for x, so we need to isolate it by dividing both sides by log of 5 minus log of 4. So we have x equals log of 4 divided by log of 5 minus log of 4. Can we simplify this by that? No. I've seen this happen many times. People simplify this by that. You cannot do that. This is not allowed because log of 5 is not being multiplied by log of 4 in the denominator. If these two in the denominator were being multiplied, then you could cancel log of 4. But not now. You have subtraction in the denominator. Okay, so if you were taking an exam where you were not allowed to use a calculator, then you simply leave your answer like that and you will receive full credit. But if you're allowed to use a calculator, you would say, or, right? We would take this one step further. We would say log of 4, let's calculate that. So log of 4. In the middle of my calculations, especially when dealing with logarithmic expressions and exponential expressions, I will keep at least 4 digits, if not 5. So I'm going to keep 0.60206. 0.60206. So I'm going to keep 6 decimal places here. So 0.60206 after rounding. Now log of 5, let's calculate that. I'm going to keep everything until 7. 0.69897. So that's log of 5, 0.69897 minus log of 4 again, which is that, 0.60206. Okay, so let's calculate the final answer here then. That divided by that difference. Okay, so we have 0.60206, right, divided by, open parentheses, take that difference, 0.69897 minus 60206 close parentheses, and we have 6.2126. So I'll keep that many significant or decimal places. On an exam, your instructor would either say, do not use a calculator, or if your instructor allows a calculator, they'll tell you how many decimal places to keep. So for now, I'm just going to keep 6.2126. I'm happy with 4 decimal places as the precision for my final answer. Okay, like that. So this one, we have e to some power that has the variable in it that we're looking for. Once again, the variable is happening in the exponent, so we must involve either log or natural log. I'm hoping that you've already solved this, by the way. So because the base is e, it's easier if we take the natural log of both sides. I know if you were here in class, as I'm recording this video, some people would be asking me, could we take the log of both sides? Yes, you could. You could take either log or natural log, but natural log makes the solution of steps easier and quicker, that's all. And you'll see why in a second. So taking the natural log of both sides, we have natural log of e to minus 2x power equals natural log of 7, right? We take the natural log of both sides. Now on the left, we know we can bring this minus 2x down and in front. So minus 2x times natural log of e equals natural log of 7. So one of the properties we had that we learned about in the last video, we know that natural log of e is equal to 1. So minus 2x times 1 is minus 2x equals natural log of 7. Okay, so if you're not allowed to use a calculator, all you have to do is say minus natural log of 7 divided by 2. And that's the final answer if you're not allowed to use a calculator. But if you are allowed to use a calculator, you would say, or we can calculate that, right? We can calculate natural log of 7 divided by 2. So let's do that. We take the natural log of 7 and divide it by 2. We have that, keeping in mind that we have a negative in front, right? So x equals minus 0.99729. I'm going to round that to 0.973. 0.973. I'm going to round that, my answer to that, like that. And either that or that. Okay. Next problem. Please solve this on your own, then come back to the video. Okay, I'm assuming you've done that. This is once again has base e. This exponential function has base e, so it's a natural exponential function. So let's take the natural log of both sides as we solve for x. So natural log of e to 3 minus 5x equals natural log of 16. Now on the left, I got to be careful. We all know we can bring the exponent down and in front, right? But I don't want you... 3 minus 5x, yes, minus 5x minus 5x. Sorry about that. Like that. Minus 5x times, I don't want you to forget to put this parentheses, because if you do, then you're going to multiply only natural log of e by this and not by that. In this case, you might get lucky because natural log of e is just 1. And if you forget to multiply 1 by 3, it's no harm done. But if it's any other term than that, then it's going to create problem. So 3 minus 5x inside parentheses, because it's two terms, times natural log of e equals natural log of 16. Now we know natural log of e is 1. On the left, we have 3 minus 5x equals natural log of 16. Right? Then let's move things around so we have positive 5x or negative 5x. It makes no difference. So negative 5x equals natural log of 16 minus 3, right? And we're solving for x, so divide both sides by negative 5. So we have x equals natural log of 16 minus 3 divided by negative 5. So this 5, we can bring it up and distribute it into the numerator, so we get rid of it. I mean, it's just dangling negative in the denominator, right? So let's bring it up and distribute it into the numerator. We end up with x equals 3 minus natural log of 16 divided by positive 5. So these two answers, if you stopped here, you'd be correct. Your answer would be correct. But usually we want to write our answer as in a combined form and as clean and neat as possible. So it's better, in my opinion, to write it so that this negative has taken effect into the numerator. So it comes up and distributes itself in the numerator. So instead of negative 3, we have 3. Instead of positive natural log of 16, we have minus natural log of 16. Okay? So even though these two are the same answer, this, in my opinion, looks better because it's more combined or more compact. So either you can leave your answer like this if you're not allowed to use a calculator, or in case you are allowed to use a calculator, either if you see this problem on a homework assignment, then all we have to do is find out natural log of 16, subtract it from 3, divide by 5. So 3 minus natural log of, let me move this up a little bit, 3 minus, there, 3 minus natural log of 16, what is that number? That's that number, divided by 5, right? Divide that by 5. We get that. So that's a small number, and this is a natural log expression we're solving x for. So I'm going to keep all the way to at least 8. So x equals 0.04548. That's where I'm going to stop. Like that. So I kept 5 decimal places. Okay. So this one is an interesting problem, this one, because notice the middle term, e to the x, and then the first term, e to the 2x. So we can rewrite this as a quadratic equation. So using substitution. So let's do that. Using substitution, right? Using substitution, let u be e to the x. So we take e to the x as u. Now let's replace back into that equation with u equaling e to the x. So we have e to the x squared is e to the x, right? So u squared is that first term, minus u minus 6 equals 0. So now we have a very simple quadratic equation to work with. We can factor this out very quickly. U minus 3 times u plus 2 equals 0. Now if u minus 3 equals 0, then u equals 3. If u plus 2 equals 0, then u equals minus 2. Right? Are we done? No. We need to solve for x, not u. So let's replace the red equation with u with each of these and then solve for x from each one. So what I mean is this. Now, from here, if u equals 3, then 3, according to this, 3 is equal to e to the x. Right? So we're solving for x. X is in the exponent. As long as it's part of the exponent, we cannot solve for it. What should we do then? We need to involve natural log. So let's take the natural log of both sides. Natural log of 3 is equal to natural log of e to the x. On the right, things are going to simplify greatly. So natural log of 3 is equal to x natural log of e. We know natural log of e is equal to 1. So x equals natural log of 3. That's one of the solutions. If u equals 3, that's the solution. What about if u equals negative 2? Well, let's do that here. If u equals negative 2, then negative 2 equals e to the x. Right? What do we do now? We have to, in order to solve for x, we need to take the natural log of both sides. Is that allowed? Natural log of 2 equals natural log of e to the x. Is that as simple as it looks? Is that allowed? No. Last time, or the time before that, we said that natural log or log of a negative number does not exist. Here, we can prove it. So, we can say natural log of negative 2. What do you think we're going to get? Error. Right? So this is not possible. Not possible. So this is not acceptable. So the only solution we have is x equals natural log of 3. Okay? All right. Do you see how the techniques that we've learned before are coming in handy? That's why I said this section is a converging point for many, many skills that we've learned, either in this chapter or the chapters before that. And that's a nice thing, because all those things you've learned before are just tools. And here, you're using all those tools to answer these questions. Okay, so here, that's an interesting problem. We want to solve for x, right? All right, so let's see how we can solve this. One thing we can do is, talking about some of the skills we've learned before, factoring, right? We can certainly factor things out. So let's do that. So we always take the factor with the lowest power if the factor has power. So the lowest power for x would be x cubed. And e to the negative 3x certainly is common for both terms. So certainly we can take it out as a factor. Times. Factoring, remember, it's the opposite of the distributive property. So I should put something here such that if I distribute this into it, we get that I get that term back. So what should I put here to multiply by this to get that back? Well, 4, right? If I put 4 here, multiply this by this, we get 4x cubed times e to negative 3x power. How about here? What should I put here such that if I multiply it by this term, I get minus 3x to the 4 times e to the negative 3x power? Well, I need the minus 3. Minus 3. What else do I need? I have x cubed coming from this, but that's x to the 4, so I need another x. Like that. Okay. So now we have these two terms that are being multiplied and producing 0. This equation equal to 0, right? So we discussed one property using the 0 product property. Remember that. If we have this situation, if we have this setup, then either this term is 0 or this term 0 or both 0. Right? Zero product property said that if you have two parentheses multiplied by each other like this equaling 0, then either this parenthesis is 0 or this one is 0 or both are 0. Well, when is this first parenthesis 0? First of all, this second term is never 0. This second term is going to get awfully close to 0, but it will never be exactly 0. So the only way this first parenthesis can be 0 is if x is 0. So if x cubed e to minus 3x is equal to 0, then x cubed must be equal to 0, which means x must be equal to 0. Okay, that's one solution of x. Right there. Again, this e to the negative 3x power can be depending on the value of x, can get very, very close to 0, but it will never be exactly 0. So the only way that this parenthesis can be 0, exactly 0 that is when this x is equal to 0. So when is the second parenthesis equal to 0? If 4 minus 3x is equal to 0, then 4 equals 3x, right? Therefore, x is equal to 4/3. So we've solved this problem without really using the log or natural log properties. Okay? All right. So moving forward to this one, these three equations on this page, page 3, please make sure that you solve these before you look at my solutions. Okay, so I'm assuming you've done that, and now you're back. Welcome back. So here, something interesting happens. Remember the earliest lesson where we discussed log functions and exponential functions at the same time? Remember that lesson? That lesson, we said that the log and exponential functions can be written in terms of one another. So if you have a log expression, you can write it in terms of an exponential function. If you have an exponential function, you can write it in terms of a log or natural log function. So let's see how we can do that. I'm just reminding you that by writing it this way. Some of you may not need this. Some of you know immediately what I'm talking about, especially if you've been reviewing previous lessons as I have asked you to. You would remember this. But just in case, this is what I mean. So here, we remember that log and natural log functions generate an exponent. Let me bring that first page that I asked you. The logarithmic functions generate an exponent. Very important to remember. That means this 3 is an exponent. If that's the exponent, what is the base? The base is written right here. The base of the log function. So if that's the exponent, this is the base, what is the result? The result is 2 minus x. Okay. Now let's rewrite this. In order to solve for x, let's rewrite this expression in exponential form. So this is the base, that is the exponent, equals 2 minus x. What do we have on the left? We have 27. On the right, 2 minus x. So we have x equal 2 minus 27. So x equals minus 25. We need to check this back to make sure that we don't end up with a negative number inside the parentheses, because remember, the log of a negative number does not exist. So as soon as you see answer, before you box it, before you say, hey, this is my final answer, check it back. 2 minus 25, it will make that minus positive 25, plus 2, 20, positive 27. So that's doable. So this is correct. So that is our final answer. And we've checked it. Okay? So here, this time, we're solving for x when we have a natural log. Once again, natural log and log functions generate an exponent. They produce an exponent. So that 3 on the other side is an exponent, because natural log and log functions generate an exponent. So exponent is equal to 3. What is the base? This is the natural log. What is the base of a natural log? It's e. And the result is 2 minus x. Okay? Now, combine all of this in exponential form. The base is e, the exponent is 3, equals this result, 2 minus x. So solve for x, you get x equals 2 minus e cubed. Okay? If you're allowed to use if you're not allowed to use a calculator, you would box this as it is. This, just checking, 2 minus e to the e cubed, you'll end up with a positive answer in here. So this is okay. This is acceptable. But if you're allowed to use a calculator, you would say, or, let's bring this back. Okay, so we want to calculate that using our calculator. So we have 2 minus e to third power, or e cubed. What do we get? We get minus 18.0855. Let me keep all that. 0855. If I'm not asked to leave my answer to a certain decimal value precision, then that's how far I keep it. But if I was asked to leave my answer to 2 decimal places, then I would say minus 18.09. I would round the 8 to 9 and leave it like that. Okay? So this answer is okay because if you plug this into here, this minus would make this minus positive. So you would end up taking the natural log of a positive value, which is allowed. So always check back into here. Make sure that your answer is not going to create an undefined expression. Okay, so next one. I hope you have your solution ready for this one. If not, please pause the video, prepare your solution before watching the rest of this. And I thank you for that. Okay. All right, so here we're solving for x. So we need to isolate the expression that has an x in it. Right, let's do that. So we have minus log of 3 minus x equals 3 minus 4, right? Moving the 4 to the other side. Then we're going to end up with minus log of 3 minus x equals minus 1. And cancel the negatives from both sides because everything is just one term on this side, one term on that side. So we can say log of 3 minus x equals 1. Right? Okay, so from this, we know that log and natural log functions generate an exponent. So this 1 is an exponent. Equals 1. To what base? The base is left blank, so it means it is equal to 10. And the result is, of course, 3 minus x. Right? Okay, so let's put it together in exponential form. The base is 10, the exponent is 1, equals 3 minus x. So let's solve this. For x, we have x equals 3 minus 10, x equals minus 7. Before you box this and say this is my answer, check it back. Minus 7, would we get a positive or negative answer here inside the parentheses? Minus x would make this a positive value. So 3 plus positive 7 is 10. So we're good. So this is a good answer. It's a valid answer. So let's box it, and I'll put a check mark indicating that we have checked it. Okay, checked it in the original equation. I hope things are beginning to make sense, and you're becoming more and more comfortable with logarithmic equations, solving logarithmic equations. Okay? All right. So the next problem, we need to solve for x in this expression. It looks complicated, but it's really not. If you remember those logarithmic properties we talked about. We have a subtraction here, right? In between this, we have 2 log expressions. In between, we have a minus. We know there is a property that says we can convert this subtraction problem to a division problem. Especially look at the bases. The bases are equal. If the bases were not equal, we could not do this. But we could not apply the property. But since they are, we can. So log of x plus 15 divided by x minus 1 to base 3 equals 2. Right? Applying those properties. So, what do we know about this? We know that, let me bring this back, since I don't want you guys to forget this. Really, it's a very important statement. Logarithmic and natural logarithmic functions generate an exponent. I've asked you many times to please remember that. So that means this log generates an exponent. So this 2 is an exponent. To what base? Base of the log function. What is the result? Okay, now put them together. You have this base to that exponent equaling this result. Right? This is clearly 9. So we have 9 equals x plus 15 divided by x minus 1. So we know that the denominator here is 1, right? So we can cross multiply. Or if you don't like to cross multiply or think of it as that, think of it like this. Multiply both sides by x minus 1. It's the same thing as cross multiplying. Okay, so we have 9 times x minus 1 equals 1 times x plus 15. So what do we have? We have 9x minus 9 equals x plus 15. So let's bring all the x terms to one side. 9x minus x. It was positive on that side. When I move it to the left side of the equality symbol, it becomes minus. It changes algebraic sign, right? Minus x equals 15 plus, let's move this minus 9 to the other side. It becomes positive 9 plus 9. So we have we have 8x here. 8x equals 24. X equals 24 divided by 8, or 3. Now, before we accept this, check back. Do you get a negative number inside any of these parentheses? If yes, we have to toss it out and we'll say no solution. Let's test it back. 3 plus 15, positive 18. We're good. 3 minus 1, positive 2. We're good. So this, we can now box this and put a check mark next to it, indicating that we have checked that answer and it's all good. Okay. All right. So the next problem, it says if 8,000 equals 5,000 times that quantity, find t. See, find t. Where is t? T is in the exponent. So as soon as you notice that the variable they're asking you to solve is in the exponent, that second you know you must involve either log or natural log functions. Okay? Then find t in years that it would take 5,000 to grow to 8,000. Okay, so we're solving for t. That means we need to isolate it. Look how many things are around t. There's the 4, there's this base, there's the 5,000. The techniques to isolating t from all of this is going to be different at each step. So we know at some point along our solution, we need to involve the log or natural log functions. But to begin with, let's see. To begin with, the first thing we want to get rid of, as our objective is to isolate t, is this 5,000. Right? So divide both sides by 5,000. So we have, let's divide 8,000 by 5,000, because the right-hand side is easy, right? You divide the right-hand side by 5,000, The 5,000 cancel out. You end up with 1 plus 0.075 over 4 to 4t power. The right-hand side is easy. The 8,000, we have to figure it out using our calculator, which is 8 divided by 5, right? 8,000 divided by 5,000. So 8 divided by 5, 1.6. Okay? So we have 1.6 on the left. On the right, as I said, 1 plus 0.075 over 4 to 4t power. Okay, now let's see what's inside the parentheses. Let's calculate that. 1.6, because right now it's two terms. We want to calculate this and combine them so we have just one number. Rather than in 1 plus that, we have just one number, right? So let's do that. 0.075 divided by 4 is that quantity. Let's add 1 to it. And we have all that. I'm going to keep all that. I'm not going to round this to 1.02 because because this is an exponential function. And if you round too much too early when working with exponential functions, your final answer is going to be way off. So you don't want to do that. So I'm going to keep all of that. 1.01875 to 4t power. Now, imagine if we didn't have these techniques of working with log and natural log functions. We would be stuck, right? Because now I would need a way to get rid of this. I see a lot of people make the error of dividing both sides by 1.01875. That's an error. You cannot, because 4t and 1.01875 are not being multiplied by each other. If this 1.01875 was being multiplied by 4t, you could divide both sides by that quantity, 1.01875. But no, in this case, this 4t is the exponent of this. So you need to bring this 4t down, otherwise you can't proceed further than this. So to bring the 4t down, we need to take the log of both sides. If you like, you can take the natural log of both sides. Okay? Natural log becomes, taking the natural log of both sides becomes advantageous if this base is equal to e. But if it's not equal to e, then taking the log or natural log of both sides leads to it's the same. It's the same. There's no advantage. It's just the steps to solving the problem are the same. They're not reduced. So it's okay. We can take the log or natural log of both sides. I'm going to take the log of both sides. So log of 1.6 equals log of 1.01875 to 4t power. Right? So the left side is really easy. We can just take the log of 1.6. Let's do that. Log of 1.6, what do we get? We get that number. We're dealing with an exponential function. I will keep at least 4 digits. In this case, even 5 significant or decimal places. And I'm going to round that last one to 2 before stopping. So on the left, 0.20412. So I rounded this one to 2 using that 9 that comes after it. So that's that. Equals, now that we have a log, we can bring this 4t down and in front. So 4t multiplied by log of that 1.01875. Okay? So on the left, we're okay. On the right, I'm going to take the log of that number, multiply it by 4, and I'm going to stop. I mean, when I say stop, I'm going to take that number and multiply it by t. Okay, so let's do that. So on the left, we're okay, 0.20412. Now, let me take the log of that. Log of 1.01875. Enter. I get this number. When I take the log of that number, I get that number. Multiply it by 4 times 4. We get that number. So 0.0322705. So I rounded that 4 to 5 using that 8 that comes after. Okay, and of course, let me not forget t. Okay, so the number you see on the left side of t is log of that number times 4. So now t is simply, we need one more step to isolate t, right? We need to get rid of this number that is next to it. So divide both sides by that. On the left, on the right we end up with t. On the left we have 0.20412 divided by 0.0322705. Right? And now let's punch that into the calculator. 0.20412 divided by 0.0322705, and that's what we get. And when dealing with logarithmic or exponential functions, I like to keep several digits after a decimal point. So I'll just say 6.325. So t, we're dealing with years, right? We're dealing with years, so let's round it to something more meaningful than that. So I'll just round it to 6.3. 6.3. Okay, and just to indicate that, because as you saw, our number, when I round it, I'm missing all those digits, right? So in order to indicate that this is about 6.3, I'm going to put this mathematical symbol like that, or tilde as it is called, to indicate t is approximately 6.3. And of course, this is in years. Okay. All right, so we have come to the conclusion of another section. I hope that you are staying true to the spirit of learning and solving all these problems on your own before looking at my solutions. If you're doing that, you will end up with a happy result in this course. Thank you for persisting through another video. Have a nice day for now, and I'll see you all next time.